All right, hi everyone. Good afternoon. So we'll get started. Today for lecture, we'll be covering the other fossil fuel energy that we didn't talk about last time. So this is the liquid form of the fossil fuels, specifically referring to oil. The lecture is going to follow a pretty similar format, going over basics, thinking about resource availability, then looking at how it's being used in technologies today, and finally looking at environmental impacts. Okay. So starting off with basics about oil. So this is the same slide from previous lectures. Fossil fuels, just as a reminder, are formed by decomposition of dead organisms, and of the three types we talked about, natural gas and coal in the previous lecture, and so these are essentially your solid form and gaseous form of fossil fuels, and the liquid form of fossil fuels. Hopefully, most people are fairly familiar with. If you ever driven in a car, ridden a bus, most of that stuff is going to be powered by byproducts of crude oil and petroleum products. Okay, so crude oil or petroleum is similar to when we were talking about coal, which has a variety of different sort of chemical compositions. Crude oil itself is not a homogeneous sort of liquid. It contains a whole bunch of different sorts of hydrocarbons. So this is kind of a rough breakdown on average, but of course, you know, there are different types of crude oil, which we'll talk a little bit about qualitatively later. But alkanes, which are your typical hydrocarbons. You've got naphthenes, aromatics, and asphaltics, and a lot of these different products within crude oil can be used to produce different end products. And so you may think of crude oil typically as analogous to gasoline, but actually we can use it to produce, you know, plastics, waxes, and a whole range of other byproducts. The alkanes themselves are specifically these long hydrocarbon chains, and they can vary in length. So the sort of shorter end ones are anything from pentane to octane, and that's what we use for gasoline. For a barrel of oil, and just as reference, one barrel of oil contains about 42 gallons of liquid. So of that 42, you're getting on average about 20 gallons of gasoline. And so those are the small end alkanes. Everything from 9 carbons up to 16 carbons. So these are a little bit more energy dense. You're getting things like diesel, like kerosene, jet fuel. They're still liquid, but as the carbon chains get longer and longer, the liquid gets a little bit more viscous, and eventually even to things like solids. So once you're above 16 carbons in the length of the chain, you're getting things like fuel oil and lubricating oil. You can really sort of tell the difference between these oils and things like diesel and gasoline, right? The viscosity of the liquid is considerably higher with the larger alkanes, and eventually you're getting to things like paraffin wax, different types of waxes for really long hydrocarbons, and so those are going to end up actually being extracted as solids. But of course, the main fuel that we're going to be talking about are these liquid fuels that are being used for transportation, gasoline, diesel, jet fuel. Chemistry of gasoline is fairly straightforward, but again, it's not sort of one molecule. It's a homogeneous mixture of small hydrocarbons. You're getting anywhere between 4 to 12 carbon atoms per molecule, and so this slide is showing a couple different molecule or molecular examples of typical sorts of compounds that you would see in a solution of gasoline. And all of these hydrocarbons, these are the sorts of things that would go into your vehicle engine for combustion and extracting energy from. So unlike natural gas, whose fundamental form is sort of just this one small molecule, it's a lot more complex than that, but it's not as sort of crazy as the molecular structures that we were showing for coal from last lecture. Okay, gasoline energy is about 45 megajoules per kilogram. Fairly uniform. Obviously, there's going to be a little bit of variation, but because the product itself is sort of refined in some way, then actually you're getting a pretty consistent amount of energy per unit or quantity of gasoline. It doesn't vary. While there is variation, it doesn't vary as much as, for example, the different forms of coal, the lignite, the bituminous, the anthracite. We'll talk a little bit more about the reserves in a bit, but this is sort of to get your mind oriented. The total reserves of crude oil, and again, this goes back to our conversation about what constitutes like a set reserve, right? So this is sort of one estimate, 1.6 trillion barrels, and the world consumes about 4 times 10 to the 11th gallons of gasoline per year. So that's 400 billion gallons of gasoline. Okay. How do we get at this resource? Oil extraction is actually not such a complex process. This is an oil derrick. So once you drill into the ground, essentially you put these long rods. They're called sucking rods that essentially mechanically will bring up oil in the zone where you have the fuel sort of located. It's basically a system of valves that open and close, and these things will continually pull up the oil resource. And so you may have seen an example of an oil derrick in real life before. They're a fairly common and fairly robust piece of equipment, and well developed after many years of exploring how to mine this resource. I should also mention that one of the other ways that we're extracting oil these days is through fracking. And so I showed the example before in last lecture about using shale resources, extracting resources from shale for gas, but actually a lot of that also will contain oil. And some shale resources are richer in oil and less rich in gas, and vice versa. And so the same method that is being used in fracking for the gas resources are also able to extract oil. Um, so when I was mentioning before about the homogeneity of oil, um, there's also these different classifications when we're talking about the way that we extract them. And so conventional oil is typically the highest quality, lightest oil, and it's easier to extract. So this is the stuff that you're getting from something like from the derricks, but you also have unconventional oils which are heavier and tar-like, and so these unconventional oils will typically have a greater quantity of solids in them, but refining them into the end products that you want are a little bit more expensive. And so that's the primary reason why most of the world oil production is conventional oil. And a little bit later on today, we'll actually take a look at supply curves for production of different types of oil, and you'll understand what that means hopefully by the end of the lecture. Okay. Oil consumption and availability. So talking about oil as a resource. So this, again, is a repeat slide from last time to refresh your memory about what we're talking about in terms of resources and resource reserves. So with the recoverable resource, this is, again, the part of the resource that's recoverable depending on your assumptions about the price and technology level. Reserves are the part of the recoverable resource that has been located but not yet used. And then the ultimate recoverable resource is the sum of everything that you've already extracted, all of the reserves, and everything that you haven't found yet. And to give a sort of quick sense of the resource estimates, here we can see from the US Geologic Survey estimates of essentially how much oil there is in the world as a resource that's available to us. And you can see that it's a pretty wide range, right? Anywhere going from 1 to 6, even as high as 7 trillion barrels of oil. And so that number that I had cited before in an earlier slide would just be sort of 1 point on this plot. And that the main sort of takeaway here is that in terms of how much oil do we have left, there's still a lot of uncertainty, right? And so we have a good sense in terms of order of magnitude. You're on the order of 1 to 10 trillion barrels, but within that there's still a lot of sort of disagreements and different techniques and assumptions that go into what we consider, what experts consider is the resource left in the world for us to extract for oil. So this is a little bit older chart, but it's a sort of nice view of the breakdown of one of the estimates by region. So approximately how much oil have we used? You can see, so the sort of solid portion of the pie is things that have already been produced, and then the white part is the reserve. And so you can see in North America, where we're located, we have produced the little more than 3/4 of our available reserve, but that the lion's share of oil is actually in the Middle East, and there is still more than sort of 2/3 left, at least at the time of this printing. Oh, I see a quick question. What is BNBL? So that's billion barrels of oil. So in this case, they're saying the resources are about 1.7 trillion barrels of oil. I think the figure that I had given was 1.6 in the earlier slide. So this is similar to the set of charts from before, looking at the same data source here, looking at the change in the quote-unquote sort of proved reserves in 1996, 2006, and 2016. So here you can see over the last several decades, actually the reserve number has sort of consistently been increasing, and there's a couple reasons for that. Some of it is discovery, some of it has to do with increasing efficiency of extraction, and being able to locate more resources in existing zones where you're already extracting the fuel. And then, as I mentioned before, as the economics of these change, the proved reserves will reflect those price changes, and the demand for different extractability levels, or ease of extractability for the fuel. So this I think this chart is maybe a little bit easier to identify sort of the available quantity of resources than in the last slide. We can actually see the breakdown by different regions, and actually what you can see is that proportionally it sort of started to move a little bit away from the Middle East over time. You can see that there was particularly large growth in South and Central America, as well as in North America, going from 11 up to 16 and 13. Part of this has to do also with the heavy development of shale resources. So the United States actually used to be a net importer of oil, and these days they have really sort of decreased a lot of the dependency on foreign oil and foreign use of fossil fuels, thanks to the exploration of shale resources. Okay, so this is what I was mentioning before about a supply curve. Okay, and so this seems like a bit of a complicated chart, so let's walk through this slowly. So on the x-axis, it's the cumulative production of liquid fuels. So essentially, as you use more fuel, you want to go from left to right, okay? Because on the y-axis, you have the cost of production. So the things that are higher in the graph are going to be more expensive. And so this supply curve is constructed by taking the cheapest things to produce first, and then going up to the next thing, which costs a little bit more to produce. And so as you consume more and more oil, going from the left-hand side of the graph to the right-hand side, it's going to get more and more expensive to make that oil. And so right here at the bottom, you have what we were calling conventional oil. And so that's the stuff that's really easy to refine, very energy dense, and is simpler to extract. And so the amount of conventional oil in so giga, so that would be billion billion barrels of oil. So this is the thing that most people are thinking about in a lot of those resource estimates. So you're getting about 1.5 billion barrels of oil, and so of conventional oil. So we've consumed maybe a third of that already, and as we continue to consume it, you'll move from you're essentially moving this dotted line from left to right. Once you run out of conventional oil, then you want to do the next available sort of resource. And so EOR stands for Enhanced Oil Recovery. It's a technique to get at sort of get at oil in a less efficient manner, a little bit more expensive, and so we can see that the cost of that increases. The reason why this isn't a flat line is because you actually have some variation in how much it costs to extract that actual resource. So it can range anywhere from $5 to $12 per barrel for conventional oil, but it could cost twice that much for something like enhanced oil recovery. Okay, I see a question. Is it because we use oils mostly from Middle East in the past, and the distribution in Middle East decreases over time? So conventional oil is available. I mean, not just in the Middle East. Actually, what a lot of people don't realize is that our biggest the country that we import the most oil from actually isn't located in the Middle East. It's our friendly neighbor, Canada. But sort of worldwide, thinking about consumption of oil, you want to use the easiest resource first. So we're sort of mining and extracting conventional oil globally, and some places are gonna, like, quote unquote, sort of run out first, right? But eventually you want to use up the conventional oil before you're doing some of this stuff. And there are reasons why we would do enhanced oil recovery and other types of things even before running out of conventional oil, because there actually is some things have or some extraction using EOR and tar sands even today, and that would have to do with sort of regional constraints, trade constraints, that sort of thing. So hopefully that answers your question. Yeah, and so the range of costs of production, there are a whole lot of factors that go into this, that could be region specific, resource specific, and also it can also take into account, I don't actually know if it's included in this supply curve, but the transportation of the fuel to the end use. So after enhanced oil recovery, so you may have heard of this, tar sands and heavy oil. So this is extraction from these. Actually, Canada has a lot of this resource, tar sands resource. This is the heavier sort of like solid sludge type thing. It's actually very environmentally damaging in terms of mining the resource. They have these sort of giant strip land essentially to extract all of these solids, and then you can actually do something called gas to liquids or coal to liquids, and this is essentially creating gasoline artificially through chemical processes. And so you might take something like methane and treat it in such a way that you can extract gasoline or diesel or jet fuel, or you can do that from solids as well, coal to liquids. And then this last one here is oil shale, which is a slightly different form of the shale that we're talking about today. Some of this actually will end up down here, but this has a really wide uncertainty in terms of how you would extract the resource from something like this. So hopefully you. If you're comprehending what's going on this slide, this gives a sort of nice overview of the different types of methods in which we can extract the oil, how much it costs, and sort of the order in which we would do them based off of the cost. And it also tells you how much reserve and how much resource is available for each of these different production methods. So it's a pretty energy dense. It's a pretty dense graphic in terms of what's going on here, but it also provides a lot of really sort of useful information to think about how to interpret all of these different aspects of the supply. Okay, there is a pretty neat concept called peak oil. So this is defined as the point where your production of your resource will peak. So for oil, the peak oil is referring specifically to when oil peaks. And most people approximate that this is about 50% of when the ultimate reserves have been produced. So going through sort of everything. Producing the remaining 50% is generally more difficult and costly. Okay, and so I'll just go back one slide really quick to talk about why this is, right? So it's sort of analogous in terms of the cost of production also has to do with the ease of production. But it's essentially why it's so cheap, right? It's easier to do. It's less refining. It's the equipment that you need to extract it is less expensive. And so as you go from left to right, not only does it cost more, the production rate tends to decrease for different types of fuels because it's harder to extract, it's harder to refine. And so at some point in the future, because we know that crude oil is a finite resource, eventually it's going to get harder and harder to produce, and that leads to a decline in the production. And so the dude who came up with this concept was this employee for an oil company. Let's see. So there's a question here. So after peak oil, is it more economically beneficial to shift from oil to other energy sources? Yeah. So it doesn't. So that's exactly the right thing to be thinking about, right? But actually, you don't even necessarily need to get to peak oil. It's not exactly at 50%. It's at every point in time as you go from sort of left to right, it's getting more expensive. And so where the break even is with a different energy source is maybe a little bit up for debate. But the idea here is right? Is it in that as production gets more expensive, as production gets more expensive, you will start to be looking for other energy sources.
Also, Alan, I think sometimes it's like the cost in in the local concept of the country. But I think Qatar have a 100% GTL refinery that work 100% with gas, and they go through gas to petroleum, and then they
Yeah,
refine petroleum.
yeah. So absolutely. So as Facundo is pointing out, and as I think I briefly mentioned that it's not as though we only do this. There is, I will say that conventional oil is the vast majority, but we are already doing things like enhanced oil recovery, tar sands, and GTL, because of like local conditions, right? Maybe you're on the like upper end of enhanced oil recovery, so it makes more sense to do like the lower end of GTL. I know that Qatar is an extremely resource-rich country for natural gas. They're one of the largest exporters of natural gas in the world. They have a lot of that resource available. So yeah, I guess it makes sense that they have a gas to liquid refinery, for local production. They make so much money selling natural gas, that they don't want to bother importing gasoline, I guess. Or I mean, I'm sure they import gasoline, but they have so much that it's worth doing gas to liquid refining or production. So for going back to this, Hubbert was the scientist who was working for an oil company, and he famously devised this sort of chart, which I think most people kind of believe is in theory correct, in that as we produce more of it, eventually you're going to reach a point at which production will decline. And that actually presents a pretty interesting dilemma, right? Because we'll show a little bit later about figures about consumption, but you could probably guess that gasoline consumption continues to increase over time. So more people, especially in like developing countries, are getting access to cars and starting to drive their vehicles. And in addition to that, the like population is growing, right? And so all of these factors are leading to a pretty consistent increase in gasoline consumption. But that at some point is going to sort of directly contradict uh, our ability to produce the oil to meet that demand. So Hubbert predicted, specifically for the U.S., not for the entire world, that the U.S. would reach peak oil for their production in the late 1960s, early 1970s. Yeah, and I think for a long time people thought that was pretty much spot on. And after that, actually, it was true that we saw a decline in production. Thinking about, okay, when is the world going to hit their oil peak? And that question is still sort of hotly debated. Some people think we'll never reach the peak, if you talk to certain folks in the oil industry. But I think the majority of people agree that it's inevitable. And so this is, one example of someone's prediction of when the peak will happen, and saying that the conventional oil peak has already happened, and then these other sources of production are also going to be decreasing pretty soon. So, right in this sort of like decadal time span, people will maybe think that we already have hit the peak, or that we will be hitting the peak over the next decade or so. Yeah, and to give some perspective on how much disagreement there is on this. So Daniel Yergin, he's an economist who thinks a lot about fossil fuel resources, and so the proved reserves, he's saying, isn't just kind of a physical concept, it's also an economic concept. And so in that idea, it's like we can affect the demand of the oil even as production starts to decline, because what ends up happening is that oil and its derivatives, gasoline, diesel, will get more expensive as there's less supply, and so less people will buy it. And there's also, so it's the combination of the economics and also the technological concepts, because they're going to let us look at resources that weren't previously available because of novel, extraction techniques. So this might be a really easy example of this would be the shale resources that happened in the last 15 years or so. In the oil and gas industry, these technologies are constantly improving. And there's a really big sort of monetary incentive to do that, right? We're consuming a massive, absolutely huge amount of oil. That's an incredible amount of money. And so, looking for more of the resources and extracting it more efficiently, all the oil companies want to do this. Okay, I see a question. How different would this be if there weren't subsidies? And so I think when you're referring to like this, quote unquote, it's sort of referring to our sort of world of oil consumption. It's probably difficult to say. I would say that the subsidies definitely allow for extraction of more sort of marginal resources, which will have a downward pressure on prices. And so subsidizing like oil production is essentially going to make it cheaper for people at the end of the day. And it'll also like some of that subsidy will be reallocated not to serve your consumers, but also to your producers. So it definitely makes, some CEOs and executives of oil companies richer. And I think that that you might be hinting at, oh, if we weren't subsidizing oil, would we be all in like electric cars or hydrogen cars or something like that? And I would um, I would I would put forth that I don't think that that's the case. That the differentiation in the cost of energy for switching to an electric car or switching to a hydrogen car is still probably a little bit larger than the price decrease that happened as a result of the subsidies. And so this isn't to say that the subsidies are a good thing or a bad thing, right? Certainly, I think that's if government subsidies were going to alternative energy types of sources, that you would bring those prices down and be a little bit more competitive. But I think that you're still fighting against a pretty sort of fundamentally useful fuel, in that gasoline is just so energy dense and hard to compete with. So the idea that we should be subsidizing gasoline, I'm sort of leaving up for debate. But I would say that our subsidization of this particular resource wouldn't have made a difference in really shifting us to another resource, at least immediately. And obviously these things take time, and had we been subsidizing other resources, maybe they would look a lot more competitive by now. But we are starting to do that, and hopefully we can see more of that happening in the near future. Yeah, so Facundo is making a pretty good point here, is that a lot of oil and gas companies like Shell, like Exxon, they are making long-term strategies to switch to alternative energies. And that might seem a little bit weird to people, that like an oil company is looking into renewables and looking into biofuels and hydrogen and electricity, all that sort of thing. And I think that they can see the writing on the wall, right? I mean, the experts who were coming up with this concept of peak oil, those were the first people who were coming up with a lot of that analysis were people in oil companies. And so if you think about the amount of money that people spend on gasoline and on oil, it's not, if we back up for a second and think at a high level, it's not that we want the oil and gasoline and diesel, it's that we want the services that those things provide. So if everyone is willing to spend a third of their paycheck on being able to move around in cars, being able to get their groceries and things delivered, and being able to fly around, the oil companies want to be able to keep that 1/3 of people's paychecks that they're willing to pay for those types of services in their pockets. And so as oil resources decrease, they want to look at other ways to be able to capture that value. Okay, another question: what do you mean by subsidizing gasoline? Does it mean that subsidizing those corporations producing gasoline? Yeah, actually, I'll be honest, I don't know exactly the mechanism with which a lot of the subsidies are happening. So I'm generally familiar with some of the quantities of monies that the government is providing to subsidize these things. But I would imagine things like leasing of land, things like helping to subsidize R&D for extraction technologies. If you add all of that stuff up, some of it is what we might consider more direct subsidization. Some of it is less direct. There are a whole slew of different activities that get funded by the government, and all of that is essentially stuff that essentially makes it easier for oil companies to produce the resource. So any money that the federal government helps to provide for making fuel production cheaper, we can consider that basically a form of subsidy, because otherwise that money should get internalized into the cost of production and be reflected in fuel prices, right? And because it's being made a little bit cheaper, in theory, it should drive prices down for the broader base of consumers. Yeah, exactly. So looking at the chat again, so anything that makes the price of gasoline cheaper is subsidization. So anything that the government is doing to make the prices cheaper is a subsidy. Okay, so back to the slides. We went on a bit of a tangent here, but that's good. People are interested and getting engaged. So besides Daniel Yergin, there are a couple other sort of big players who have opined on what they think about peak oil. Some, as I was mentioning, not everyone thinks that peak oil is real. Some economists think that you have higher oil prices and more improved technology, it essentially means that you can produce oil sort of for the foreseeable future. A lot of geologists disagree because there's fundamentally like just this there aren't these like new discoveries of reservoirs to be found. And because of what I was saying with declining production and growing demand, at some point you're going to peak for conventional oil production. One last sort of opinion by this geologist basically has a pretty simple explanation, right? The glass starts full and ends empty. The faster that you drink it, the quicker that it's gone. And so, yeah, there are these little caveats about the economics of it and about technology availability, but we know that it's a limited resource, and we're drinking from the glass, and eventually it's going to be gone. So to look at considering the uncertainty, we can do kind of a quick, easy calculation. Again, this is that equation before about looking at the ultimate resources for cumulative. So looking at what's been produced, what's in the reserves, and what we have left to find. If we assume that peak oil happens when there's 50% left, we can look at peak oil. So oil use is in these units per year. So it's 1/2 the ultimate minus cumulative production divided by annual usage. That's what AU stands for, annual usage. So basically, this is how much we have. This is how much we consume every year. We can figure out the year in which peak oil happens based off of the total amount. And so based off of different people's estimations of what they think the reserves are. So for example, this geologist says 2.1 trillion barrels. USGS has a low estimate of 3, high estimate of 4. We've already used 900 billion barrels of oil. We use about 30 billions barrels of oil per year. And so if we use that equation, then in theory, we could be hitting peak oil within, say, 5 years or up to something like 70 years, right? And so at that point, production will slow down, prices will increase. And it can still be pretty difficult to tell whether or not we've hit peak oil already. But these are, as you can see, a pretty wide range of uncertainty and estimates here. Okay, thinking about conservation, how much could our demand of the oil postpone hitting the peak? So I haven't talked about CAFE standards yet. These are fuel efficiency standards that basically require cars to be cleaner. For those who've looked at project descriptions already, you may have a better sense of what this is, but essentially it's in the US regulation that makes our cars more efficient and thereby makes us consume less fuel. And so, over the next decade or so, you can see the resulting decrease by having a standard 40 mpg, and then a higher standard 55 mpg will decrease it even more. We can have a renewable fuel standard. So we'll talk about all of these policies sort of later on in the class, but the rough sense of what the renewable fuel standard is it makes the fuel itself cleaner. You blend in ethanol with gasoline. And so you use essentially less gasoline because you're displacing it with some other fuel such as ethanol. If we transition to fuel cell vehicles, and then there's also this smart growth trajectory. Actually, I'm not actually even sure what goes into this. And so here you can see different trajectories. If we implement any sort of combination of these things, we can see how that affects the consumption of oil over time. And we're going anywhere from 14, 15 million barrels of oil a day down to 4. But even in the sort of most optimistic sense, it's going to be difficult to completely transition away. One other way we can decrease our demand, pandemics. So this was a pretty interesting chart that was shared among some of our colleagues recently. Weekly demand for fuel is the lowest it's been in almost 2 decades, and that happened basically overnight. This is kind of we don't want to have like pandemics to decrease demand, but it's a pretty interesting effect that we're seeing already, and I think that has actually continued to decrease. Couple more slides before we hit our midpoint break. So U.S. oil production, as I'd mentioned before, from the Hubbert curve, the guy who originally came up with peak oil was doing that analysis specific for the United States. And so U.S. oil production, it's pretty it's pretty agreed upon that, or it was agreed upon that production had peaked in the 70s. But actually, if we include a couple more years, right? So this slide actually only goes up to maybe the mid 2000s, right around when shale was beginning to get developed. We can see that production has shot up again. So even the concept of peak oil is a little bit fuzzy here. So I see, so a clarifying question. So at the beginning, you mentioned the conventional and unconventional oil. So we can transfer from unconventional oil to conventional oil by refining. So I wouldn't quite put it that way. Conventional oil versus unconventional oil are like essentially different types of oil that are, so conventional oil is what we would think of as the crude oil that you get in these like barrels of oil, whereas unconventional oil is a little bit more like, it's almost kind of like sludge. It's more like tar. So the forms of the oil themselves are a little bit different. We don't convert unconventional oil into conventional oil directly and then do the same refining process. You just take the unconventional oil and you refine it to your end products through different methods. So the flow of it is like conventional oil to all your products like gas and diesel and jet fuel. And then for unconventional oil, it's not that unconventional oil gets refined into conventional oil and then gets made into gas and diesel and so on and so forth. It's unconventional oil going to gas and diesel directly, but the process in which you do it is a little bit harder and then a little more expensive. Okay. So hydraulic fracking accounts for half of the US crude oil production. And so we can see the oil production quantities here, and this has led again to kind of a direct contradiction to the peak oil concept, at least in the US. Okay, sorry, quickly to follow up on the question. So it depends on the end products we're going to get. Yeah, so it's not that it depends on the end products, but you will typically get different end products. yeah, so the unconventional oil is simply a different form of oil that we're extracting. Also, so the amount of transport of fuel, because we're doing all of the stuff from a lot of stuff from shale, is now also increasing, and so the where we were importing a lot of the conventional oil before, now we're doing a large quantity of production ourselves. A lot of that is located in sort of the Midwest and southern regions of the United States, whereas most of the populations are on the coast. So there's a large increase in the transport of fuel. And this will have implications, as we'll see in a little bit, about environmental impacts. Here, this is a map of shale resources worldwide. I'd shown a map of specifically the US and looking at some of those resources. But now that shale has become a little bit more widespread and available, we can see that there are lots of other regions around the world that are able to take advantage of this. Last bit, thinking about oil price shocks and recessions. We won't talk too much about the implications of supply versus pricing, because the market for oil is really it's not so straightforward. This is not like a perfectly competitive environment, and so even though you have a pretty set amount of demand, supply and prices are actually set by a cartel. And so OPEC, which is essentially a monopoly, we call it a cartel because there's multiple participants. They are able to effectively control the price of oil because they control so much of the supply. And this has led to things like price shocks, and so that's sort of the main point of this figure here, is that we can see in the red really sudden increases that are somewhat artificial, having to do with pricing set by OPEC. And there's actually a similar type of thing happening for price shocks. Actually, when you have sort of extreme events that do affect demand a lot, you can see a change in the prices. It's pretty. I think in general it's a little bit more rare for price shocks to be happening on the demand side, because our travels are so sort of well known and set. But in the case of like a global pandemic, we do see a massive decrease in demand, leading to a drop in oil prices. And so it's the lowest, oil and gasoline is the lowest it's been in 2 decades. So if you need to refill your car with gas, now is a good time. And I think besides, well, okay, well, let's stop here, and then we'll pick up a little bit more on economics of the fuel before we get to its use after a 5-minute break. So let's pick up at 1:14, and in the meantime, I'll sit around here if anyone has any questions or wants further clarification on specific issues. I'd be happy to chat about it.
Hi, Professor. I'm Josie. I have
Hi.
a question about the homework set one in the problem 3. I think it's like we have a number is like 10,000 kilowatt per hour. So I was wondering what would be the significant figure on that number like.
Yeah, so I did go through the homework to try and be as consistent as possible. So let's see. Let me just open it up so I can make sure that we're on the same page here. Yeah, I guess based on this, it looks like most of them would be listed at one significant figure. Although, I'll probably be a little more flexible on this one. So, 1 or 2 sig figs for the answers for question. Did you say? Oh, I'm looking at question 4. You said question 3, didn't you?
Yeah, it's like 10,000. Is that the one? Because I remember in the lecture you say, well, if, for example, I give you a number 1,000, so I'm not asking you to do a 3 or 4 figure, then
Yeah.
okay, I thought we make the same assumption, like, or about
Yeah, you're right.
10,000.
So here, so technically the correct sig figs would be 1, but I would actually say that that I would be fine with doing 2 sig figs here.
Okay, thanks for the clarification.
Yeah. Okay, I see another question also regarding the homework. So on homework for question 3, should we calculate the amount of electricity needed, assuming that all the prison's gasoline energy requirements to be met by electricity? So actually, no, the gasoline listed in question 3 is actually not relevant to the problem. So you don't actually need to worry about the gasoline. And then on question 4, should we assume a discount rate for the life cycle analysis? Yeah, actually, that's a really good question. I think that when I had put it together, let me take a look just to make sure. We didn't have a discount rate and that everything was treated uniformly, but I guess the correct way to do it would be with a discount. But for question 4, we would accept an answer without a discount rate.
Yes, I think you don't need to assume the discount rate, because there's one point that you have it, and there's another point that you don't need to use it.
Oh, really? Is it?
Yeah.
Oh, you mean with?
Yeah, because it's in the past.
You mean specifically within question 4 or throughout the homework?
Yeah, specific for the question 4, like
Oh.
because it's the first three years that you have it, and then it's like considering when you start production. So
Okay. Yeah. Yeah. So we'll be really flexible with that one. Okay. Let's get back to the lecture and continue on. So I think the last thing that I want to talk about with the economics of oil is that there are a lot of hidden costs of oil dependency that people don't typically think about and are not actually internalized in the price that you see at the pump. And so this is costing us money in different ways. And so transfer of wealth from United States to oil producing countries. Okay, and so we're losing some domestic revenue, right? Because we're transferring that wealth to other countries. Loss of economic potential due to oil prices that are elevated above competitive market levels. And lastly, disruption costs caused by sudden and large oil price movements. And so if, for example, OPEC decided to just hike the prices up really high, yes, we would maybe decrease our consumption a little bit, but still, the price setting isn't sort of being directly tied to demand in this particular example, and that's causing a large sort of economic loss in revenue. So if you added up all of this stuff, then there have been some studies. So I think this one was actually from I'm totally blanking on the lab. Oak Ridge National Lab in Tennessee did this study back in 2005 that estimated the total costs of oil dependency. All of these macroeconomic costs could be as high as $8 trillion and on the order of hundreds of billions of dollars in single years alone. And that doesn't even include all the environmental damages and military spending. So these are all things that are kind of important to consider, and these may actually even be when we were talking about subsidies. You can almost think of the not internalizing these costs as part of the subsidies for oil, even though oftentimes we wouldn't measure it in the same way. So this might, to put it a little bit more concretely, this might be something like, if we went to war with the Middle East because of oil, if that were some of the sort of underlying reason, then one thing you might say is that, well, we spent these hundreds of billions of dollars on our military to go to war, to engage with Iraq and Afghanistan on the battlefield, spending all this money for the war, when we could have been using that money for for education or for alternative energy or that sort of thing. And that you might consider as to be another sort of subsidy for gasoline. Is this transfer of money that could have been spent on other things, but was actually being spent on oil, right? And so that particular example may be a little bit more controversial, but there have been actually a couple peer-reviewed scientific studies that have looked specifically at this question. And so a lot of these studies, if you include all of the externalities, all the economic externalities I was talking about here, about the hidden cost associated with these three issues, if you include the military costs and also environmental damages and impacts, you could double gasoline prices or even more in some cases. Okay, so that kind of wraps up sort of high-level thinking about pricing and economics and supply of oil. So here we'll talk a little bit more about how they're being used, how they're being applied. Okay, so this is the supply chain going from your oil to refinery. So you can either domestically produce your own oil, or you can import the oil, and the oil has to go through a refinery to produce your end products. So in this particular case, we'll think specifically about gasoline. That gets stored, and then you can have imported gasoline as well. So the refined oil is domestically refined whereas imported gasoline is refined somewhere else. That all gets transferred through pipelines and through other modes of storage and transportation to ultimately what are known as these bulk storage terminals. So these fuel terminals are kind of the endpoints right before you go from the trucks that deliver them to our retail stations, so the gas stations that you're used to. And to give you a sense of how many fuel terminals there are around, in California, I believe there's about 32 or 33 fuel bulk storage terminals for gasoline, and you've got other terminals for different types of fuels. And sort of across the US, you're talking about on the order of a couple hundred terminals. Okay, and so the gasoline makes its way all the way from the oil down into your gas station before it enters your vehicle, and then it magically transforms from gasoline into movement, right? Except we'll talk about that actual process. So similar to when we were talking about coal and when we were talking about natural gas, thinking about how it actually gets combusted, how it gets sent through the turbine to produce electricity. In this case, it's a little bit different. The fuel goes through an engine before it gets translated into motive energy. Again, this isn't a mechanical engineering class, but this we're going to walk through a pretty basic schemata to see how an engine works. And I think that this is maybe a little bit more specific technologically, but it's important to have some of this understanding even in a policy context, because we're actually going to be talking a little bit later about specific technologies that are thought about in the policy and regulatory process that can help improve some of the existing technologies or in the past technologies for engines, and so having a sort of basic understanding of how this works will be handy to get a better grasp of the importance of regulation in improving some of these things. Okay, so this is a neat little graphic that I've been using for a couple of years now that describe the operation of a 4-stroke cycle as well as a gasoline engine. So there's 4 stages here. You've got an intake stroke. So this whole diagram is depicting a single piston in your engine. In the first stage, you've got what's called an intake stroke. And so the piston goes down, which sucks air into the cylinder when the intake valve is opened. And at the same time that the air is getting sucked in, you have this item over here called fuel injector, which injects aerosolized fuel, aerosolized gasoline into the chamber of the piston. In the second stage, called the compression stroke, the intake valves will close and the piston will move up. And by moving the piston up, all of the stuff that was in the chamber of the piston from stage 1, the fuel and the fuel air mixture, will get compressed at a higher pressure. And this allows, by increasing the pressure in this way, it allows for better power and efficiency. And then you have, in the third stage, a spark plug. And the spark plug will ignite the compressed fuel air mixture, which is the thing that's actually doing the work. So stage 3 is where the actual work is happening when you combust the fuel to move the piston down. And then in the fourth stroke, the piston comes back up, and what happens on that stroke, called the exhaust stroke, it pushes the combusted mixture out through the open exhaust valve. And so this whole process is sort of carefully designed and calibrated so that you can sort of squeeze as much juice out of the fuel as possible, right? You want your piston to be operating at a certain temperature, at a certain pressure, and you want the whole mechanism to be, compressing it to exactly the right sort of conditions. And then in the combustion, you want to essentially explode as much of the fuel in complete combustion as possible. And then in the exhaust port, you want everything to get, you want as much stuff to be removed as possible so it doesn't sort of continue to contaminate your next stages. So it's kind of a simple process, but it's been really sort of fine-tuned to be as efficient as possible. Okay. This is a nice little diagram of the holistic portion of the engine. So this is a four-cylinder engine, which means that you've got those 4 pistons that we were seeing in the last in the last slide. And what you can see happening is that each of the cylinders is operating at a different stroke cycle, and so it can be set in continuous motion. Okay, so what's actually going on here? So as the pistons move up and down, they are rotating this thing on the bottom called a crankshaft. And so you might be wondering from the last slide, well, how can I so accurately time when I'm opening the valves, when the fuel is getting injected, and when the spark plugs are happening? It's actually all in a mechanical timer. So as the crankshaft rotates, it's moving this belt, which moves this thing up at the top called a camshaft. And the camshaft has these cams that are attached to it, which are rotating. And as you can see, these are mechanically timing this whole process so that it's opening the valves and injecting the fuel and having the spark plug go off, all in sync with the movement of your pistons. This is I guess we don't really call it this that often for a 4-cylinder, but this is a V4. So the V4, V6, V8, V12, that just refers to the number of pistons or cylinders here. And as you can imagine, the more pistons and cylinders that you have, the sort of smoother the rotation is. So the analogy that I like to kind of use is, think about what it would be like if you were riding a bike, okay? And so there's 2 arms on your crankshaft. So the part that you're pedaling on, right? So there's 2 arms, and those arms are almost kind of the equivalent of your pistons here, right? As you push down on the pedal, that's kind of the power stroke that's happening. So think about how you would be riding your bike if you only had one pedal arm. So you would need to push down, and then you would need the momentum of that whole cog system to be rotating to get to a position where you can push down on your one foot again. And so it makes it a lot more jerky, right, if you only have one crank arm. So that's kind of the idea here. So the more pistons that you have, the smoother the rotation of the crankshaft will be happening. Okay. So don't worry too much about the details of this. Again, this might be if you were in a more sort of mechanical engineering concept, thinking about the thermodynamic cycle. In other words, so a thermodynamic cycle is having a cycle where you return to an initial stage, and there may be some energy input, and this is leading to changes in temperature and changes in entropy conditions. So you've got 4 strokes that are corresponding to different portions of the cycle. And so this, in theory, we can work through the math and look at how to move through this diagram and think about what's the sort of maximum or ideal cycle efficiency. And so for something like the Otto cycle, which is a basic cycle that represents essentially how 4-stroke pistons work, and I'll just quickly mention that, you know, engines today use slightly different cycles that are all sort of foundationally built off of the Otto cycle. So if we do all the math and we figure out energy input and the technical amounts of work that you could get out of it, then you could, in theory, get cycle efficiencies as high as 56 to 61%. And these are almost sort of physically impossible to get in reality, because you've got things like friction and imperfect conditions. You can never maintain exactly the right temperature and pressure, right? And so the typical average efficiency is for internal combustion engine vehicles is actually ranges between 25 up to 35%. Okay, so I briefly talked about fuel injectors. These are basically things that spray the aerosolized gasoline into the cylinder at exactly the right moment. But there's also variation in the fuel types, right? So as we discussed, gasoline isn't always like a completely homogeneous mixture, so you can get different quantities of compounds and molecules within the gasoline. One of them is the relative amount of octane fuel within gasoline. And so you may have seen these ratings before, 87, 89, 93. That refers to, that is a reference to the amount of octane that's in the fuel. And so it's a pretty big misconception that there is actually a correlation with performance and efficiency regarding octane rating. That's actually not true. You can, as long as your engine is compatible with any of these fuels, then you're essentially going to be getting about the same efficiency. The reason why certain vehicles will prefer higher octane ratings is in order to be resistant to this thing called auto ignition. For a lot of higher power engines, luxury vehicles, the engines can run a little bit hotter, and the conditions within the piston themselves are a little bit different. And if you have more octane, then you can avoid this effect called auto ignition, which happens when the cylinder gets too hot or certain conditions in the cylinder happen, which will cause it to combust the fuel before the spark plug ignites it, which makes it a little bit inefficient and also throws it off the cycle a little bit, and you get this loud noise called knocking. And that's usually not very good for the engine. So the only reason that you would need to get the higher premium gasoline is to avoid that effect. But you would need to be using a specific car with a specific engine that would require basically that higher level of octane. Okay, last bit here. Thinking about other components of the system, you've got your air intake, and then you've got lubrication of oil for your engine so that everything can move with reduced friction. Without oil, you're going to be essentially damaging your engine as things get hotter than they need to be, and there's more friction, less lubrication. Okay. So let's, I'm actually going to skip ahead. We don't need to know all of this stuff. There are some electrical components as well. For the vehicle, the spark plug wires are connected to a distributor so that you can get the timing right. And so that part is also connected mechanically. You can actually see a little rotating device inside here. And then there are electrical components in your vehicle as well. So think about power windows, think about your like radio, all the digital devices within the vehicle. That is supplied power from a battery. And for the majority of cars, it's going to be a lead acid battery. Yeah, it's actually pretty interesting. Even in something like a Prius, which has a large nickel metal hydride battery, or used to have nickel metal hydride. These days, they use these small lithium batteries. You'll actually still find the presence of these big lead acid batteries. And so the lithium ion batteries and the nickel metal hydride batteries are being used for a lot of the hybridization systems or electric vehicle systems, actually for powering the drivetrain. But then this lead acid battery is sort of on the side to power the small electric components and systems in your vehicle. And we'll actually learn a little bit more about electric vehicles and how they work in other lectures. And the last part here is the exhaust. And so this is the part that gets sucking out all of the combustion byproducts going through a catalytic converter as well as a muffler. And this system is actually really important when we think about emissions. And actually the catalytic converter exists a lot thanks to regulations in California. So again, a lot of this stuff that we're talking specifically about how the technology works is going to tie pretty importantly into a lot of regulatory design decisions that we'll cover in future lectures. And lastly, the way that the motion of the crankshaft, right, which is the thing that gets rotated from your vehicle engine operation, it's translated to motion and motive power is ultimately through transmission and drive shaft. These things are tremendously complicated. In fact, I know at some, in some schools, you could actually take entire classes just on how a transmission works. And so we're obviously not going to get into that. It's basically a system of complex gears that allow you to translate the rotation of the crankshaft into rotation of your wheels. Yeah, and actually some people get confused about this. When you are driving a car and you're stepping on the pedal and you're looking at your at the RPMs, right, that go up from on 0 up to 8,000, 9,000. Those RPMs are referring to the rotation of your crankshaft, not of the rotation of your wheels. Your wheels do not spin that fast. And so the way that you can go from the thousands of RPMs rotations per minute into the rotations of your wheel is through the transmission. Okay, So the last thing that we'll talk about are environmental impacts. And so I think we've spent a fair bit of time thinking more broadly about combustion of the fuel going to emissions and pollutants and air pollution. And so we will talk a little bit about that, but I think that there are a couple sort of interesting things to think about specifically with oil that we'll cover in a little bit more detail here. So the effects of drilling and producing oil. So even sort of the extraction process will lead to some impacts. Disturbing land and marine ecosystems. So oftentimes when you're doing the surveying, the seismic techniques used to look for oil under the ocean can have ecological impacts on ecosystems for fish, marine mammals. Drilling an oil well on land will often require clearing an area of vegetation, and so you can see that here, sort of right in the middle of forest. You got to build a road to it, and you got to make the pad as well for the location of that particular excavation site. I'll also note that actually it was pretty interesting when I was in grad school, as I had mentioned before, that was the time period right when a lot of the shale was really getting developed in the Midwest / East Coast, in the Marcellus Shale, particularly which was near where I'd went to school. They were expanding a lot of shale extraction resources, and I remember we had a guest lecture by an ecologist who was studying this and looking at how we tend to think of the impact, the clearing of this land as the biggest impact, right? That you're cutting down this land here, which is no good directly, obviously, because you're removing trees and you're disrupting probably the local ecosystem. But actually, there's this other effect that could be even larger, which is the continuity of the forest apparently is really important. And so as you start to make these patches throughout the forest, then sort of the effective sort of boundary size of the forest gets decreased in a really sort of non-linear way, and it can have these really big fundamental impacts on the ecosystem that stretch like way beyond just the clearing of this area. And so that's an important thing to consider. There are ways to help mitigate this. There are, for example, instead of using seismic techniques, you can use satellite systems and remote sensing to discover oil reserves without necessarily just drilling what we call exploratory wells just to see if it's there. Mobile and smaller slim hole drilling rigs, and so this is making the process sort of a lot more confined, so that you need less area to do your drilling activities. And then the horizontal drilling, especially in shale, makes it possible for a single well to produce oil from a much larger area, whereas you would see in maybe the more conventional oil resources, you would just have these oil derricks spread everywhere to tap into the conventional oil resources. By being able to go horizontally, you can have like one excavation site that can reach a large area beneath the ground. Concerns with hydraulic fracking, fracturing. So as we had talked about this before, but fracturing rock requires a really large amount of water, and they use lots of hazardous chemicals. And what ends up happening with that water is they just put it into these ponds here. And I think that that's still somewhat of an unsolved issue. Any leaks and spills of the fracturing fluids can lead to contamination of water sources. So here you can see, I think I had mentioned this before, there were a bunch of incidents where certain towns, they would have flammable water. So this guy's holding up a lighter to this sink faucet, and you can see it's just combusting some of the fuel that's contained within the water. Probably don't want to be drinking that stuff. And then injection of the wastewater can cause earthquakes. I've mentioned that before as well. And then you can also have really large impacts from things like oil spills as you transport, or even in the extraction process for things like deep sea drilling. So oil spills are the results of accidents at oil wells or in the transportation, either in pipeline, ships, and trains and trucks. Oil spills contaminate soil and water. They have huge ecological impacts. And there are constantly sort of developments of standards to help reduce this. But unfortunately, a lot of that happens sort of after the fact. And we can point to that historically. So hopefully, I think most of you guys have heard of some of the more major ones that have happened in your lifetime. So I'm thinking specifically about the Deepwater Horizon event. And so that happened, totally blanking, although I do have a slide about that. That happened in 2010. But to give you a sort of high level perspective of that, to give you a sense of like how much oil got spilled over the course of 5 months or so, you had a little more than 4 million barrels of oil, which is kind of like a really astronomical number or quantity of fuel, covered hundreds and hundreds of miles, eventually diffused out throughout the ocean, very large ecological impact. But kind of the punchline that I like to say when describing this is that actually, so if you think about that quantity of oil and that quantity of oil coming out over the course of 5 months, to give you a sense of how much oil and gasoline that we use per day, it's about the quantity that we send up into the air through combustion of gasoline in one day is equal to the total amount that was spilled over the 5 months. Or actually even a little bit more. This is the 5 largest oil spills. We can see the Deepwater Horizon one at 4.1 million barrels of oil. U.S. oil consumption, this includes not just gasoline, but also diesel and jet fuel and a whole bunch of other uses. But just consumption of gasoline is about equal to the amount from Deepwater Horizon over 5 months. So again, to reiterate, like what we spilled into the ocean over a 5-month time period is what we combust and send into the air every single day. So quite a lot of fuel. So a couple notable ones, in Santa Barbara, there was a blowout on an oil rig that led to 3 million gallons of crude oil. This was back in the late 60s, in 1969. At the time, it was the worst oil spill in the United States. and it prompted a sort of modern environmental movement. Actually, Earth Day, the origin of Earth Day was actually a follow-up to the Santa Barbara oil spill, and that's actually something that is still recognized and celebrated today. And you can see the coverage for those of you who are familiar with the Santa Barbara region, LA region. This is the extent of the oil spill, how it spread. Probably another one that folks have heard of, the Exxon Valdez oil spill happening in the Prince William Sound in Alaska. And again, this is a map of that. The spread after about 2 months, people were finding large quantities of oil hundreds and hundreds of miles away, so 500 miles away. So, these things really are large ecological impactful events, and are really far-reaching and can affect ecosystems over huge amounts of territory. Yeah, even though that this is particularly bad and was one of the biggest ever in U.S. waters, it's actually doesn't even really make the list in terms of largest oil spills by volume. As I was mentioning, there's regulations that help to reduce some of these impacts or to avoid some of these impacts, but unfortunately, a lot of these things happen sort of after the fact. So the Exxon Valdez oil spill that happened resulted in Congress passing the Oil Pollution Act of 1990, which basically required all oil tankers to have double hulls. So even if you ruptured the first hull, there would be a second hull that would be intact. And there have actually been some studies indicating that this has already reduced the size of oil spills by 20% in tank barges and 62% in tanker ship accidents. So offshore drilling, so this accounts for about 16% of the oil in the US. Presently, you're only allowed to do offshore drilling along the Gulf Coast and a little bit off of Delaware, but in Alaska, it's fairly open to offshore drilling. There is a moratorium set against offshore drilling to protect a lot of natural ecological areas. So in the Gulf, as we had just mentioned, there was a big blowout on the Deepwater Horizon, largest oil spill ever to occur in U.S. waters, and eventually leading to about 4.9 million barrels of oil leaking over the course of 5 months. This picture was happening shortly after the blowout event, and the barges couldn't actually end up putting out the fire, and so the whole rig collapsed and ruptured the pipeline extracting the oil, leading to the eventual big leak. So here we can see basically where you're allowed to do offshore drilling in gray. And so these are program areas for potentially where drilling could happen. But right now, you're only allowed to go in the light gray area. And actually, there's even a moratorium in the eastern Gulf of Mexico against offshore drilling. In Alaska, in the northern portion of the Alaska, the northern border to the ocean, you're allowed to drill. And then there are planning area boundaries, again, that are potential areas for drilling, but currently don't or aren't allowed to. And then you have a moratorium here where you're also not allowed to. Yeah, so there's a question, does moratorium mean no more drilling sites or no more drilling at all? So moratorium means you can't do anything. So no drilling, no new sites. Wait, actually, sorry, I'm getting myself confused. I think moratorium means no new drilling, but existing ones you can still run. I'll check on that. My memory is a little bit hazy right now, but I'll confirm. But more recently, there's been a proposal to open up waters to offshore drilling, and so there's some regulation, draft proposal for program areas for future drilling sites. Yeah, so there's a question here. What about the offshore rigs in Santa Barbara and LA? Yeah, so in these program areas, you have some leases that are allowed to occur, because there isn't a moratorium, but there are some rules about additional leasing and opening up to drilling for new resources, and so that all of that is not allowed. So the newer regulation actually is potentially going to be opening up all of this territory for offshore drilling, and so there are proposed program areas that will be opened up in these sort of corresponding years, if the regulation ends up getting passed. And so I actually don't follow this too closely, but there could potentially be a lot more offshore drilling in the future. From the land-based drilling perspective, some of the key oil and gas regions, so we looked at some of this before. You've got your shale and regions where you're extracting oil and natural gas. And so one of the things to notice here is that these resources, again, are like located away from a lot of the populations along the coast, which means that you have to have transport out to those regions, and that oftentimes will result in accidents. And so here's a map that displays historical transportation accidents on train lines. And that has led to community action in other parts of the country. But one of the things that you'll note is that, we care about the ecological and environmental impacts of these things, but oftentimes they're not really correlated with the people who are directly impacted. So crude oil train accidents, so something like you're seeing here in this picture, and again, sort of after the accident happened, the US DOT has proposed new standards for braking controls and speed restrictions to help reduce the amount of accidents. Air pollution impacts, we've talked a lot about this, but the combustion of any fossil fuel is going to lead to air pollutants. So the localized pollutants that are leading to degradation of local air quality are things like particulate matter, hydrocarbons, nitrogen oxides, carbon monoxide, and sulfur dioxide. That'll lead to things like acid rain. And a lot of these air pollutants and toxics, especially volatile or organic compounds, the EPA estimates are responsible for half of all respiratory cancers caused by air pollution. And so, especially with vehicles, that's located like where people live, right? Because people are driving them. You're on the corridors for transportation, whereas electric power, the power plants may be located farther from population centers. Not always the case, and we'll talk about that a little bit when it comes to equity concerns. But it sort of stands to reason that we are sort of highly affected by transportation emissions locally. From a greenhouse gas perspective, petroleum is the largest contributor to greenhouse gas emissions. It used to be from the electric sector, the combination of natural gas and coal, but gas has sort of increased because of the shift from coal to natural gas, and transportation overall has overtaken other sectors in terms of total emissions. But as a fuel category, petroleum has sort of always been the highest CO2 emitter. And transportation is the thing that's responsible for growth in oil use. So when we break down how oil is used, transportation's share has continued to increase as there's more demand for gasoline. And this is sort of worldwide. Asia is the fastest growing market for oil. I think in a lot of the more developing countries, as people get richer, access to transportation, which is a good thing, is also leading to higher sort of demand for the fuel. And that's leading to higher and higher emissions. And so this is a problem that's not going to be going away anytime soon. You are going to have, there are projections that are showing, even though the OECD countries in the Americas are higher in consumption of transportation fuels today, Asia will be overtaking us in a lot of the projections out into 2035. And that's going to mean more emissions over time. And so this is sort of our backdrop baseline scenario for thinking about alternative energy fuel sources, thinking about electric vehicles and hydrogen vehicles, and how we can reduce our environmental impact. And this is the motivation for a lot of the policies that get put into place these days, again, which we'll go into a lot more detail. Okay, so I am a little bit over time. This is the last slide for today. So we'll end here. And in the meantime, I will sit around for just a couple minutes in case anyone has any other questions. Otherwise, I will see all of you guys on Zoom next week.